My name is Mike, and today we're going to be discussing diesel and after-treatment devices. What I'm about to share with you today is a presentation I usually present in the field. I added one module at the tail end of this presentation where it involves sales. We're going to make this presentation available to you online. I get a lot of questions. I forget, it's like a 36 meg file, but they'll make it available for you. Just delete the last module and you'll have something you can present to your customers. And it's diesel and after-treatment devices. And this is a hot spot. This is a subject that's been prevalent in most of the accounts we'll walk into, whether it's in a dealership or in a fleet world. So when we discuss in sales, I'm going to be discussing as well as internal and external sales, selling to the dealership and the dealership selling to your customers. And I'm going to break this down to three subjects here. Your first subject, the first area of focus is going to be soot and its root causes. Then a second subject will be discussing its impact on after-treatment devices. Now, whether that's through regen frequency or component failures, we'll discuss that. And then once you have an understanding of that, the last subject line, which again is the last module, you can just delete that module and you'll have something you can present in the field. That's selling the product. And how do you sell it to your customer, and how does your customer sell it to the end user? So let's get started. A lot of material here. Again, it's going to be recorded, so if you take the time out to review this afterwards, I think it'll be archived online. You can watch it again and again and again if you're tired of looking at me. But soot. Usually when I'm in a field, I start off with a slide, something like this, and it says, have you seen this before? And if you're in a shop or with your technicians in the diesel world, you're going to get a bunch of head nods. That's often something they're saying. That's soot. Now, whether the soot's going to be located in the EGR coolers or EGR valves, and you may have seen this yourself. Sometimes you see the soot located inside the intake manifolds, the runners, or grid heaters. Now, a grid heater is something that's used to heat the air as it enters the engine. They use this in place of glow plugs. This is typical Cummins, which you see a grid heater. Same soot in a grid heater or intake manifolds will eventually go through the cylinder and up inside the exhaust system. So you see it in your DOCs and your DPFs, diesel oxidation cats and diesel particulate filters. Now, for those of you who are not familiar with diesels, we'll take time to expound upon those components later. But the filters themselves, once the soot starts to accumulate in them, and it is a filter that's located in the exhaust, just like a fuel filter for the fuel system or an air filter. That filter has to be changed or cleaned at regular intervals. But if you don't, it gets to a place that becomes plugged, and they call that face plugging. The engine usually shuts down, you got no power on the side of the road, and this is where you get a tow bill installed. So when I'm talking with you or your customers, I usually ask them questions like, what's the primary contributing factors? What do you think causes the soot? And you'll hear replies like it could be the engine or the engine's design. And maybe it's the oil, could be maintenance history. You're talking some of the decision makers that are out there, people who've been around a while, they'll say, well, it's not the engine itself, it's the application of the engine. And that's what I like to focus on, especially if you're dealing with an OEM. It's not the engine's fault, it's the application of the engine. And often their hands are tied, they can't change that. Because diesels aren't meant to idle extensively. So if you can think in your mind's eye, anything that would be idling, such as an ambulance or a transit bus or a school bus, anything that does extensive idling, that will contribute to the soot buildup. So they're often calling upon the OEM to change the algorithms in the computer programming, to force these things into regen more frequently. Those are all contributors to soot, but they're not the primary source of soot. And as a BG rep, if you're calling on your customers, you need to understand this. There's a huge opportunity out there in the marketplace to see an increase in sales in some of our chemicals. The 109, the 112, the 244, diesel injection service with 229, or now the 9300. All good tools. We're going to discuss them, their application, and what benefits they bring to the table. So if I was going to ask you, what do you think the primary cause of soot is? This is your answer. And this isn't from me, or this isn't from our guys in the lab saying that oil is the primary contributor to soot. Most of the soot, whether you find it in the EGR or EGR coolers, or in the exhaust systems like the DOCs or the DPFs, or in the intake manifolds, wherever you find that soot, even on the turbos, backside, the turbine, that soot is primarily oil. And if that's the case, then you have to ask yourself a question, well, how does the oil get into the exhaust? How does the oil get into the intake? We're going to discuss that. But first, we have to confirm that it is oil. An overwhelming majority of the time, the soot you pull and you look at, it can be determined it's oil through laboratory tests. Now, if you've ever done an oil analysis before, where you take the oil sample and you send it to the lab, I'd strongly recommend that you grab a sample of the soot too from the same engine. And I don't care if the soot is from the EGR or EGR cooler, or if it's from the DPF or the intake manifold, it's the same source. And I'll show you why in a moment. Take that soot with the oil, send it to the lab, and have them perform an analysis on the soot. That analysis is called an ICP metals analysis. Now, unfortunately, I don't think Polaris performs that test, but I know our guys here in Wichita do. You get Shane and Dustin will oversee that, and Don and Mike. We do have this ability to perform the ICP metals analysis. The ICP metals analysis will actually give you a report that looks very similar to an oil analysis. And for those of you who haven't seen a report, what I've done here is I've taken the time out to show you what those metals are. If you're looking at the left-hand side, you see metals starting off from copper, aluminum, chromium, going all the way on down to phosphorus, sodium, and zinc. The very second column, or middle column, that's the soot. And when they test that soot, they actually look for the metals with that soot. And if you sent the soot in with the oil from that engine and you compare them side by side, you'll see majority of the soot are oil-related deposits. So there's a test out there that, again, I want to bring to your attention, you should be mindful of and utilize this. It's called the ICP metals analysis. The reason for the test is it allows us to provide empirical data to your customers to show them that it is oil that's inside those system components. So it goes back to the questions I asked earlier. So how does oil get into system components? How does it get into the exhaust or the EGR coolers? There's an important test which you're probably familiar with from the GDI if you've been around for a little bit. Our GDI classes, we talk about that NOAC volatility test. This is something we have a competitive advantage on. Oil is not oil. And this is a test that's not normally performed during an oil analysis. You have to request this. In that oil sample bottle that I showed earlier, not enough. You need at least 16 to 20 ounces of oil in order to have this test performed. It's called a NOAC volatility, and it's an ASTM test. It's not a BG test. It's an ASTM, American Society of Testing Materials International, global organization. And that test itself determines how easily the oil evaporates. Now, when you've done your GDI demos, you remember that there were maximum limits of 15%. Well, that's true for all the oils that are out there, except one, your 15W40 oils. The cut point, pass or fail, for your 15W40 oils is 13%. And unfortunately, most of the oils that are being brought in for tested exceed that. Now, to explain what oil evaporation is, simplicity. I will usually have a bottle of water or a can of gas if I'm in front of your customers. And I'll take the cap off that bottle of water and simulating a can of gasoline. How long would it take for you to be able to smell those fumes? Within minutes, seconds, depending upon how close you are. Those vapors that are inside that gasoline are petroleum vapors that are starting to evaporate. Oil is a petroleum. Diesel fuel is a petroleum. And when those oils start to evaporate, those vapors have to go somewhere. So the manufacturers have made some changes on these engines to capture those vapors so they're not released into the atmosphere. On today's engines, the gasoline engines, they're running so clean that when you're filling up your vehicle with fuel and you got the nozzle in a fuel tank, you're generating more hydrocarbon emissions, hydrocarbon being raw gasoline, unburned. You're generating more hydrocarbon emissions filling your fuel tank up than when the engine's running properly what's heading out the tailpipe. That's pretty clean. Now, so we look at these deposits, we have to determine what's the root cause of these deposits. And one of the tests that we use is, again, the NOAC volatility test. 16 to 20 ounces, send it to the lab, new oil, virgin oil. Also send to the lab a sample of the soot with the used oil from the engine that you got the soot from. And then you'll be able to tie the two together, and now you're making your case for the use of 109 or 244. So let's get into these deposits and how do they end up in the exhaust system components. This particular slide here, I can camp out for a while. I can print a picture off, I can laminate it, and I can sit and talk for an hour if you'd like, and I'm not going to do that to you, so trust me. But this particular slide gives you a bird's eye view of what's going on inside the diesel engine. And I'm finding off when I'm traveling in the field, most of our reps don't fully understand the diesels. They understand the impact our product has, but they don't understand really what's going on. And to me, it's important for you to have an understanding of why you're selling the system's components, whether it be a 9300 or 9700, or you're going to suggest that diesel performance oil change with the 109, 112, 244, 245, if you like, which is for the high pressure common rail systems. But the system itself is here is laid out before, and you see those numbers 1, 2, 3, 4, 5, and 6. We're going to go through each one of them. Your first one that I'm looking at is number 1. That is actual something you've seen often in earlier presentations with gasoline engines. That's blow-by gases or compression, if you will, escaping past the piston rings. So when the engine's running and the piston's moving up and both the intake and the exhaust valves are closed, sometimes the compression will escape past the rings and enter into the sump. When I say sump, I'm talking about the engine's crankcase where the oil's at. That's number 2. So now I've got elevated sump pressures. Those elevated sump pressures have to be vented. On a gasoline engine, we use PCV systems, positive crankcase ventilations. Diesels, until recently, within the last decade, used to vent these through downdraft tubes, if you would imagine in your mind's eye, rather than having a PCV system recirculating it back to the intake. They used to have a tube to come up the side of the crankcase, and there's a little road draft tube, and it created a draft and pulled all the oil vapors out. And you can sit there at a stoplight and watch the trucks next to you pissing oil on the ground. Well, they can't do that anymore. EPA's cracked down on that. Those are hydrocarbon vapors. So now the diesel engines are required to take those oil vapors, the pressurized sump pressures from blow-by gases, getting past the rings, down in the sump, they're recirculating it through number 3, what they're referring to as a crankcase ventilation system. Now, a crankcase ventilation system or PCV system on a gasoline engines can be located on the side or front or top of the engine. And their sole purpose is to capture those vapors and recirculate them back into the intake. If this system gets plugged, it'll turn a check engine light on. If the system's plugged and the vapors can't breathe, escape, it'll blow gaskets out. And that's when you see these diesel engines with valve covered gaskets. And I've seen at times so much pressure inside these sumps that has blown the dipstick out of the dipstick tube, which is why some of those dipsticks are locked into place. A lot of sump pressure there. So when you take those vapors and are recirculating them back up into the intake manifold, and in the intake manifold as the engine running, it'll draw those vapors down into the cylinder, it would burn those vapors and send them out into the exhausts, which we're looking at number 4. Now once it goes into the exhaust, there's 1 of 2 paths it can take. One path is heading up into the EGR circuit, which is a small amount, and the other path is heading down into the exhaust. Looking at the EGR circuit itself, that if those oil vapors are recirculated back through the EGR or EGR cooler, that's how we got a lot of soot load inside your EGR valves and EGR coolers. That soot's primarily oil vapors, as well as fuel, but primarily oil vapors. And those oil vapors are again recirculated back into the intake manifold, along with the crankcase ventilation system. Now, what's a challenge here is that guys often will turn around and look at the intake manifold with the diesel engine running. They'll pull the cold air tube off and they'll see oil accumulating inside there, and they'll automatically say 109 will fix that. And I'm going to show you this again later. So if you pull that cold air tube off the intake, you see oil in there. It could be through the crankcase ventilation system. On your Fords, especially in the 6.7 liters, if the air filter is plugged, it's got to draw air in from somewhere, so it's going to draw in through the crankcase ventilation system. And if you're looking at the little flow meter inside the air filters, they're useless. Don't look at those. So good maintenance is important. So the air filter has to be inspected as well. Keep these things in mind when you're looking at these vehicles and you're performing your demos. Now, the other gases that are not going through the EGR circuit are going out the exhaust system. And that's where it goes out to the DPF or the DOC or the SCR. So the soot, whether you're looking at it from the EGR coolers, to the DPF, or in the intake manifold, the grid headers, it's all the same source. So I don't care where you get the soot from, take the soot with the oil, send it to the lab, and have them analyze it. And if we can tie the two together, we are building our case for the use of our products. I hope that makes sense to you. If not, watch the video again. It'll make sense to you later. Now, let's focus a little more on this EGR valve, the EGR and what its function in life. And there's a lot of misperceptions underneath the EGR valve. Its purpose. Now, purpose of the EGR valve is to lower combustion chamber temperatures. It's not meant to reburn the exhaust gases to help clean up the emissions. Often hear guys doing their demos, and this is something they're saying, it's not true. If you're not careful with your word tracks, and if you don't fully understand the system, you're doing this as a sales presentation. Somebody out there in the field that's knowledgeable hears this, you just lost credibility. So please understand the EGR system itself. And I'm going to explain it to you. Keep it in simple terms for you. Its purpose is to lower combustion chamber temperatures. And the reason why is at approximately 2,500 degrees Fahrenheit in that combustion chamber, you're going to create an emission. That emission is called NOx, N-O-X. Proper terms is nitrogen oxide or oxides of nitrogen, which is a blend of chemicals, NO, NO1, NO2, NO3. That's why there's a small X there. NOx by itself isn't harmful. However, when you're back filling up your fuel tank with gasoline, any hydrocarbon vapors and ultraviolet rays from the sunlight, the three combined create ground level ozone. And ground level ozone is where you have ozone action days with people with respiratory problems, your eyes start to burn. Ground level ozone isn't good. I live in Atlanta and I'm heading down Interstate 20 as I'm going towards the city. We're about 1,000 feet above sea level. But the city sits about 920, 950, depending upon where you're at. So it sits in a valley even though we're 1,000 feet above sea level. And I can see as I'm driving down Interstate 20 to the city, this haze sitting there within the city. And that haze, they have ratings for it, and they call those ozone action days. Is it a yellow, an orange, or a red? And on severe ozone action days, they actually ask you not to fill your vehicle's fuel tank up until after hours, when it's late in the evening, so there's no ultraviolet rays to reduce NOx emissions. So if we can prevent that smog, if we can prevent NOx from being created by lowering combustion chamber temperatures where you reduce that, that's the purpose of the EGR valve. Now, what does a diesel engine need to ignite the air fuel charge? It doesn't have a spark plug. Heat. And the heat's done through compression. So to me, in my mind's eye, or any diesel tech that's out there will tell you, well, if I'm trying to cool the combustion chambers off, but I need the heat from the combustion chamber to ignite the air fuel charge, it's like having a campfire, you start sprinkling water on it. So all your wood doesn't burn. That's soot that starts to head out the tailpipe. But it's something that's required for NOx emissions or soot, so there's this delicate balance going on in the engine. And we're here to get these engines restored back to like new conditions so they run at peak performance. Now, the EGR valve itself, if you can see the same type of schematic, and you'll notice on the exhaust valve it's slightly open, that's in the yellow. And as exhaust gases escape through the cylinder and being pushed out through the tailpipe, some of those exhaust gases will be recirculated back up through the EGR and the EGR coolers and be recirculated down into the intake manifold. Now, those are burnt gases. And that's going back to your campfire. If you've burnt wood and you got ash left, you can't reburn the ash. Now, yeah, you may have a little tinder or two, some charred fuel in there, but its primary purpose is to lower combustion chamber temperatures by displacing oxygen. And if I reduce oxygen, I reduce the fuel, and I've taken an explosion that was occurring inside the cylinder from boom, size of an M80 to boom, down to a firecracker. And by reducing the size of the explosion, I reduce the heat that's been generated. But going back to what I mentioned earlier, you're dampening that fire. So you may have soot that starts to accumulate in these EGR and EGR coolers, because again, it has to head out to the tailpipe. So our manufacturers are scratching their head, how do we circumvent this? And we got guys putting delete kits on it. Please don't put delete kits on these EGR systems. It's illegal. 1990 Clean Air Act. Volkswagen just got their hands slapped. Now, we're not the police out there, but be mindful of this, that they're really cutting down. It's a $37,500 fine per occurrence for the business. And it's a $3,750 fine for everyone that's in that business, from the lady who answered the phone to the person pushing the broom to the tech that installed it. So please avoid that. Don't be involved with any of that. Now, another contributor to oil getting into the exhaust system are turbochargers. This is something we can't fix. Once it's broke, it's broke. We can't fix broke. So the next time you're pulling a cold air tube off, look at the turbocharger. And you see before you a picture of a turbocharger, a little fan wheel in the center. The little fan wheel spins at a very high RPM, and what it's doing is it's drawing fresh air in from the air filter. But if you're looking at the turbocharger, you see there's oil accumulation there. That oil accumulation, it's not my words. This is something that's used often in the field. It's called turbo slobber. Like a baby slobbering all over itself. And all the oil that's accumulating there inside that turbocharger is going to be pushed into the intake manifold. So where's the oil coming from? In order to understand that, we have to look inside this turbocharger to see if we got residue of oil coming into it and look at the air intake tubes. Let me explain to you turbochargers and how they function. Before you're looking at it as a schematic of a turbo. You've got the air filter drawing fresh air in. That's the turbine wheel that I showed you. And it's pushed down through an intercooler. Because once you push air in under pressure, it starts to heat it up. So now we can heat the air going into the intake. We don't want that. Going back to NOx emissions. So we got to cool the air charge off, so you send it through an intercooler. That's located in front of your radiator. So if I can take the air and push it into the engine, and then you see a similar fan on the other side of the turbo, that's going to blow it out the exhaust. The concept is the quicker I can get the air in, the quicker I get the air out, the quicker the car goes. The more oxygen I can push in, the more fuel I have, the more power I get, within a balance before you blow the engine up. So this turbine actually has one impeller. I think I just lost my microphone here. Hopefully, am I still on? So this turbocharger itself has got one impeller located in the intake, one impeller located in the exhaust. On the intake side, you've got an impeller wheel, and on the exhaust side, you've got the turbine wheel. These two wheels are hooked together through a shaft, and that shaft itself rotates. It can rotate over 125,000 RPMs. That's high speed. Oil lubricates that shaft. And if you're not maintaining these systems properly, and that seal starts to go because the bearings are worn out, oil will piss out that turbo and go in through the intercooler and be sucked into the intake manifold. My question to you is, will 109 fix that? No. So be mindful of that. At this point here, I'm often asked that, hey, can our 9300 or the 9255 clean turbos? We never send chemistry through the intake side of that turbo. We always go after the turbo. However, on the exhaust side, you notice it has to go through the turbine wheel. Yes, you might be able to clean some of the soot off on the exhaust side. Is it designed to? No, but I've seen it happen. That's a question I'm often asked. Now let's take a look at this turbo on a vehicle, a different schematic, same setup. That turbocharger itself still has air that's being pushed in through an intercooler, and the intercooler is located in front of the engine. So if you have turbo slobber and all that oil starts to accumulate, if you will, what do you think you'd accumulate at? You had oil being pushed out from the turbo, it starts to accumulate in the intercooler. And that oil accumulation sometimes gets so heavy, I've seen some manufacturers put a petcock in the bottom of the intercooler to drain the oil out. Now, if you're looking at the other side of the engine on that blue tube, you take that cold air tube off, you actually see oil spitting out of there. So much so that we were just recently here in Wichita, within 15 minutes, I got a puddle of oil sitting in the ground. 109 is not going to fix something like turbo slobber. So please be mindful of that. If it is compression, blow-by gases past the ring, and oil volatility, yes, it will. Now, another contributor to soot is the fuel. The fuel itself. Normally when I'm out there in the field and as a sales rep, I'd always have two samples of fuel, one that looks pretty nasty and one that looks clean. We've all done this before. Whether it's a mason jar, myself, I use a little 8-dram vials because they're easy for me to transport, carry them in my shirt pocket if I had to. The one on the left is obviously bad, but let me draw your attention to one on the right. Most people look at that and say, yeah, fuel looks good. However, you may have particulates floating in that fuel. What you got before you is a picture, or if you will, a slide, showing a cross-sectional area of a human hair. The human hair diameter, if I plucked one off and I sliced it in half, was approximately 80 microns. If you take a look at the larger circle within that human hair, the one at the bottom, that's 15 microns. That's your standard fuel filter. If you're looking at the middle dot, that's usually 5 to 10 microns. That can cause damage to your fuel systems. Your high efficiency fuel filters, and if you know our 9700 tool with the 020 little white hockey puck, that's a 2 micron filter. That's a high efficiency fuel filter. So my question to you is this: if you can take that human hair and slice that in half and look at the cross-sectional area, and then you look at the center dot and you see that's 5 to 10 microns, next time you're looking at the fuel sample, can you see if you've got those particulates floating in there? Now, unless you're the Terminator or you're Steve Austin, the Bionic Man going back from the 70s or 80s, you can't see that. You need to send it to the lab and have it tested. So my question comes to you is where is the source of particulates? How does something like that get in there? Fuel additives. Some of your competitors out there are using ferrocene, which is an iron-based fuel additive. Other sources could be from dispensing pumps. This particular slide, if you went to the gas station again, you got the nozzle and the fuel tank, and as you're filling the vehicle up with fuel, you'll see that the plate in front of it has a little key. You pull the panel off and you'll see there's 4 square holes. Unbolt them, you can pull a strainer out and you got a bunch of coffee grinds floating in there from the underground storage tanks. That's another source. I think you got a question here. Is there a question?
Yeah, we had a question come in. Is this why Ford went to water-cooled turbos?
One of the reasons.
Okay, we also
cool it off. Next question.
Another question. Will it help clean the VNT?
Would it help clean, I'm sorry?
The VNT?
Variable vane turbos. On the exhaust side, it's not designed to, but anything that's burned in the combustion chamber has to head out to the exhaust, and we have had some success with that. Not designed to, and I wouldn't go there selling that. If it happens, it happens. If it doesn't, it doesn't. But never send any chemistry through the impeller side of the turbo, which is on the intake. Always go after that. Don't want to send any liquid through it because you'll knock the turbo out. Another question?
Yeah, one more. Is the turbo axle lubricated with engine oil?
Yes. Yes. That turbo shaft is lubricated with engine oil, which is why it's important to have a good quality engine oil there. Yes, absolutely. That's what helped to us to build our case for 716 or 714, something that doesn't oxidize because of the high speeds. And I share this with you because if you're focusing on a 9300 tool or the 9255 tool and just trying to clean the EGR or the DPF, please be mindful that the same soot that's in the DPF or EGR is also in the intake manifold and on the turbine side of the turbo. Same soot. So whether having turbo failures, EGR cooler failures, or DPF failures, or soot load inside the DOCs, it's all related, same source. Any other questions? Okay, we're good to go. Now, another contributor, going back to the fuel and particulates floating in the fuel, other than rust that can be occurring from the underground storage tanks, is something called asphaltene. That's a black fuel filter. Now, I'm not referring to microbioorganisms or bacteria or humbugs, what some people like to refer to them as. Your black fuel filters themselves is actually a black substance that starts to accumulate on your fuel filters, and this can happen within 5 to 10,000 miles. It's prevalent on a lot of these common vehicles we're seeing out there with high-pressure common rail systems. Let me explain to you what's going on here and what we offer to repair this. Asphaltenes is what the correct term is. Now, if you've been around a while, you know that we do fuel system seminars. And during the fuel system seminars, we show the refining process where you've got a barrel of crude that's being refined, and the lighter ends are gasolines, from 87s to 89s to 91 octanes to kerosenes to diesel fuels. That's a barrel of crude you have on your left. And in the 70s, a barrel of crude, barrel being 42 pounds, weighs about 42 gallons, weighs about 300 pounds. It's all a man can lift up and put on a truck at the time. A barrel of crude in the 70s, you probably have about 54% of it straight run fuel that can be used for various applications, whether it's diesel or kerosene or jet fuels or gasoline and so forth. The bottom of the barrel, the heavier crude, was so heavy it wasn't usable as asphalt, greases, tars. But through today's technology, through catalytic cracking and hydrocracking, the heavier bottom molecules, they're combining it with the lighter and top molecules and coming up with a cocktail mix of fuel that's being sent to you, which is why the shelf life of diesel and gasoline is much shorter than it was years ago. So once this fuel is a cocktail mix, hydrocracking and catalytic cracking, and combining these two lighter ends and heavier ends together, when you put them through a fuel system that's exposed to a lot of heat, the fuel molecules start to break apart and accumulate the heavier ends on the filters. That's asphaltenes. Now, it could be asphaltenes, if you think of the word asphalt like on a road, but it's teen, E-N-E-S. Now, your typical white filters within 5 to 10,000 miles look like that. And what's going on these modern diesel engines, they're becoming more like gasoline engines, where you're looking at common rail systems where you pull the fuel from the lower right fuel tank and through your fuel filter and fuel pump. It's sent up to the injectors, and when the injectors turn on, it sprays fuel into the cylinders. Now, gasoline engines always had a pressure regulator recirculated back to the fuel tank. Diesel engines that came up recently, and they call it a common rail system, high pressure common rail system. And high pressures are heating the fuel up because you raise the pressure, you raise the temperature. Now, it's high pressure common rail systems are returning these fuels back to the tank superheated. And the fuel's heating up, and it's going through what's properly called depolymerization, or it's returning back to its original state. And you got those little oil droplets or asphalt droplets that are floating in the fuel that plug up and get into the fuel filters. What's our solution? 245 instead of 244. 225 HP instead of 227. 232 HP instead of 230. That'll help to minimize this, to keep this from occurring, to prevent depolymerization from occurring. Now, this is all happening internal in the fuel system on the vehicle. This isn't something that's been introduced externally, which is why Coordinating Research Council, CRC, has got bulletins out there saying within 100 engine hours, we can have internal diesel injector deposits that are occurring inside the fuel system. And these deposits are wreaking havoc. We have some manufacturers we're working with within 20 engine hours, brand new vehicles, brand new pieces of equipment, 20 engine hours, injectors are going bad. And it's not because of corrosion, erosion, or pounding the injector, which does happen. This is in addition to that. This means the fuel itself is creating issues. Now, the injectors, if you see, the top needle is much larger, had more mass, more weight, as opposed to the newer injector's bottom needle. And what's going on is thinking in your mind's eye that, hey, I've got a locomotive heading down a rail. And as the engine starts to go down a rail, you can power the engine down. And as it powers down, it takes a lot of energy to slow that engine down, as opposed to the bottom injector nozzle, which is a 10-speed. The heavier nozzle, if there were any deposit there, would pound through that deposit and the engine would still continue to run. But these smaller needles are more susceptible, so any type of deposits will knock these things out, which is why we're continuously looking at fuel additives here in Wichita to come up with a proper solution for today's vehicles. Technology has changed, so please be mindful of that. Now, switching gears here. This soot that's starting to accumulate, whether it's in the intake manifold or in the exhaust system, the OEM's aware of that. They have solutions. They're redesigning pistons. Matter of fact, Cummins on their ISX has got something referring to an APR kit. An APR stands for anti-polishing rings. It's re-sleeving the cylinders and putting rings on it with low top pistons Because that one piston, the picture there you see on the left, has got a gap at the top of the piston, and you get carbon packing in there, and it starts to scratch or score these cylinder sleeves, which contributes to additional blow-by gases and exacerbates the problem. We have another question.
Yeah, we have a question. How many miles with the 716 or the 714 could we get?
How many miles can 716 and 714?
Yeah.
Why didn't you catch the last part?
How many miles the 716 or 714 could we get?
I mean, in service intervals, is that, if I understand the question correctly, how much life can you get out of our oil 714 or 716?
I think that's what they're asking.
Okay, if that's what you're asking, and if I understood your question correctly, there is no cookie cutter approach. And here's why. Some of you diesel engines that are out there, example, Max Force 7s, are notorious for making oil, which I'm going to discuss in just a moment. And what I mean by making oil is you get fuel dilution in a sump. And so we get fuel dilution down in a sump, and the engine's oil level starts to increase, as opposed to having hash marks saying it's low, add 1 quart of oil. They actually have a notch in the dipstick saying there's too much oil in the engine. It's making oil. Fuel dilution. Is that the oil's fault? Did the oil break down, or was it contaminated? So when you're asking a question for 714 or 716, can we extend service intervals? Possibility. It depends upon the application and the engine. We need to look into that. Anytime you recommend extending service intervals, always based upon an oil analysis. Anytime you recommend extending a service interval, based upon an oil analysis, and it'll give you the go or no go. Now, as far as making oil and blow-by gases, that's our next topic, which brings up to blow-by gases. You're familiar with this. Piston rings. You got 3 rings in this particular picture. The top ring is your compression ring. Your middle ring is more of your wiper ring to keep the oil off the cylinder walls. Your bottom rings are your oil rings. These rings are designed to be sealed against the cylinder wall. There should be no space between the rings themselves and the cylinder walls except for a boundary film of oil. If there gets the ring stuck and they're stuck on a piston and it creates a gap between the piston and the cylinder walls or the cylinder liners, you're going to have oil that can get up into the cylinder, which can contribute to the soot accumulating inside the exhaust system. But you also have fuel going down into the sump. So it's important, and you may have seen this before, that the piston ring is seated against the cylinder wall or cylinder liner. Now, piston ring itself, the top ring is a compression ring. The compression ring has a gap of about 0.02 of an inch that allows the compression, the pressure from the cylinder, to get behind the ring to force the rings out against the cylinder wall. They have to force the rings out. Any deposits there will prevent those rings from being forced out against the cylinder wall. Now, if you're looking at the picture, you see where it says 0.02 of an inch? That looks like a pretty big gap, doesn't it? I got a piece of paper. I don't know if y'all can see that. That piece of paper, that's 0.04 of an inch thick. The gap between the piston ring and the piston is half the thickness of this piece of paper. So if you can envision in your mind's eye deposits that are accumulating inside that combustion chamber and being pushed into the EGR valve, if it gets stuck in these rings, you're going to have these rings allowing blow-by gases down in the sump, fuel down in the sump, and oil back into the combustion chamber. So it's imperative we keep these rings clean. Not an option. The top side of the rings we're using 244 or 245. The bottom side of rings we use what? 109. EPR. Not an option. Now you got guys that are neglecting the EPR and doing it every other oil change. Guys, if I had to sacrifice something, I would not sacrifice 109, especially in today's diesel engines. Now, there's something I often see out there. You see gasoline engines. This is a gasoline engine where you see the chamfer on the bottom of the ring and you see it's cut differently. This is more like a wiper blade going up and down, being the top piston ring in a gasoline engine. I'm not talking about the wiper ring in a diesel. It's your top piston ring. So if you're doing your GDI demos, guys, that's not on diesels. The middle ring acts like a wiper, but your top ring itself is not chamfered, is not cut for being a low tension ring, because these engines are excessively high pressure in the combustion chamber. So it's imperative that we keep these rings clean. That's why we have our services that are out there. with 244, 245. 9300 does a good job of cleaning the top side of rings as well. And on the bottom side of rings, the EPR. And when you're done, use the DOC. Now, DOC itself, to me, the way I like to describe it, if you can envision in your mind's eye, cold flow improvers are paraffin wax and number 2 diesel fuel. And you get wax gelling on a filter. And when those wax particulates start to coagulate or collect together, it plugs the filter up. That's the same thing our DOC does for the engine oil. It has soot scatter technology, prevents those things from coagulating and creating hardened carbon deposits that'll cause damage like you see there in a picture. So now we got that soot, and that soot goes down into the after treatment devices. And there are 3 basic components in the after treatment devices. Now, they're a DOC, a diesel oxidation cat, not 112, not talking about diesel oil conditioner. Your SCR, which is selective catalyst reduction, and a DPF, diesel particulate filter. The DOC has been out there since the 70s on diesel engines. The DPF come up at 2007 and a half, say 2008, whereas the SCR for NOx emissions comes up about 2010 and a half going to 2011. These 3 components have 3 separate functions, and they can be located in different areas. This picture of a Class A truck where the SCR is located on the top, and underneath it you see the DPF with the DOC, and you have the DEF, the fluid, located for the SCR in the side tank there. Now, the SCR itself is to reduce NOx emissions, not prevent it. And if you remember, the EGR is meant to prevent NOx emissions by cooling the combustion chamber. The SCR helps to reduce it after it has been formed. A bird's eye view picture here, schematic, and on this picture you'll see the very first one's the DOC diesel oxidation cat. It's usually first in the exhaust stream once it leaves the engine. The DOC starts to heat up, and then you may either have the SCR and the DPF, or in some applications the DPF and the SCR. The SCR is again for NOx emissions, and DPF is a filter. Now, to draw a parallel for you, to take you from something maybe you're familiar with to bring it to the unfamiliar. For those of you who have been around a while, this is a picture of a gasoline engine. This is not a diesel engine. It's a picture of a gasoline exhaust system there. And you see in the exhaust system where you've got all the hydrocarbons and carbon monoxide and NOx emissions heading out the exhaust pipe going from the left to the right. You have 2 beds there. Your first bed there is designed to reduce hydrocarbon and carbon monoxide. Then it's got a pipe, if you will, where you see air injections, as a little red arrow will point into the center of the catalytic converter, and then your second bed is for NOx emissions. Both beds had noble metals, expensive metals, platinum palladium in a front bed and rhodium in a back bed. But years ago, and it's been out there for a while now, we had an air tube going into this exhaust system. An air tube comes from an air pump or air fingers. An air tube would often be broke off and guys would pound the tubing shut, or the air pump would lose a belt. This has been out there for a while. If you're familiar with this gasoline engine, you got a DOC, diesel oxidation cat, on the front, even though it's in the same housing, with an SCR on the backside, but instead of injecting air into the exhaust stream, we're injecting DEF fluid. It's been out there, the technology, for a while. This isn't something new. It's something they've been working on and they've evolved to over time. Once again, the SCR's purpose is to reduce NOx emissions, whereas the EGR is meant to prevent NOx emissions. And if you remember, in the EGR, it cools the combustion chamber. So if we could reduce the EGR by having more SCR, you can actually help to reduce some of the soot that's being created inside that engine before it heads the tailpipe. That's the purpose of the SCRs. And now we're going to get into the DPFs. Your diesel particulate filter is just as its name says, it's a filter. Envision in your mind's eye a fuel filter. And over time, the fuel filter has to be serviced and changed. It's the same thing as the DPF. Over time, the DPF is going to have to be serviced and changed. It's not like a toilet bowl that once it gets plugged, it has an overflow that allows it to drain back in the tank. There is no such thing. This engine will shut down. The DPF is designed to capture soot and burn that soot off. Now we have to get into the term soot, and we'll define that. But your DPFs have an efficiency rating, and your efficiency ratings in some of your earlier applications were 2007 to about 2010 were about 80 to 90% efficient, which means 10 to 20% of the soot can still escape past there because it wasn't a very good filter. Now you get some of these newer trucks are out there from 2011 to 2015 are 90 to 95% efficient. which means 5 to 10% of the soot can still pass through the filter. 2016, they cracked down even more. Now they're 95 to 99% efficient. They're pretty efficient filters that are capturing soot. And soot is the black particulates you see in the exhaust stream as a truck's going down the road. That particulate matter, if you breathe it in, can cause cancer. So they have to capture the particulate matter to prevent cancer from occurring. How they clean these things off is through something called regen. And what I mean by regen or regeneration is they're regenerating the filter. They're going to heat it up and heat the filter up through usually one of 3 different methods. I'm categorizing this for you to keep it simple. One way to heat it up is passively. In a passive regen, when you hear that in the field, simply means that the truck is heading down the interstate and there's enough heat generated inside that exhaust that it'll burn off that soot and help clean the filter. Whereas an active regen is where the computer or the PCM comes into place and it actually has to turn an injector on, whether it's in the cylinder or in the exhaust, and we're delivering fuel directly into the exhaust and have it like a furnace fire up and burn off any soot that's accumulating in it. The third one is referred to as a forced regen. Your forced regen is when it goes into derate, and derate means the truck has to slow down, can't move anymore, done, stock side of the road. You got to push a button on the dash and you got to let it go through regen. This could be a road call with a technician and a laptop. Trucks that are commonly using work trucks to do a lot of frequent stop and go, like your ambulances, your school buses, and mass transits, sanitation companies, excessive regens. Some of the OEMs have got their solutions. They used to, on the MaxxForce, put a filter, if you will, on there, a plug after the filter, and prevent exhaust gases from flowing through it. The exhaust gases, if you see that big, large area is what the exhaust gases used to flow through, and they're forcing it all through that little hole right there. And then it'll raise the RPMs up to 2,500, 3,000 RPMs, and you're watching that exhaust system go cherry red and the overflow tanks start to swell up. That scares me. That's not a forced regen. It actually damages the substrates. And you'll see in this particular substrate in DPF a little plug and ash tube, if you will, that's sitting up over here. And when you have damage done to the DPF, you start to burn holes in the DPF. Then the exhaust gases and the soot that was supposed to be captured pass through, and you see, like on the right-hand side, or a school bus. You should not see that soot. You should not see the opacity heading out that tailpipe. And myself, when I'm going down the interstate, whether it's on a truck or if I'm going to perform a service on a vehicle, one of the first things I'm looking at, especially in the 9300 service, is that tailpipe. If you see a tailpipe that looks like that, that's not a candidate. There's something wrong with the DPF. That DPF needs to be replaced. Or maybe it was already replaced, they just didn't have a chance to clean the exhaust out. So be mindful if you're going to select a vehicle for 9300 and you're asking for the worst case scenario, and you walk by the tailpipe and you see soot in a tailpipe or plastered on the back end of a transit bus or the side of a tractor trailer, not a candidate, because the exhaust gases are passing through the DPF and allowing the soot to escape. You can't fix that. You can't fix broke. Those have to be replaced. The DPF itself is a filter, and a filter is designed to capture the soot and allow gases to pass through. And over time, the filter needs to go through a regen to burn off that soot. So when you get a brand new filter and you got the full length of the channel on that filter for the capturing of the soot, you'll see that the first time you buy this vehicle, within the first 20,000 miles, it may regen once a week. Then you get to about 25,000 miles, it's regenning twice a week because of the ash accumulation in there. Soot burns off, ash remains. Then we're getting to 50,000 miles, it's burning 3 times a week. Then 4 times a week, now it's regenning every day, sometimes twice a day before this truck goes into regen, goes into derate and you ain't moving it anymore. Now the soot itself, if you can envision your mind's eye, is a ball with little particulates of ash in there, or if you will, a watermelon with watermelon seeds. Those watermelon seeds can't be burned. Those are metals and elements that won't burn off. That's ash. So when we go through regen, you're burning off the watermelon, but what you have left is the ash. So if you send soot to the lab, you burn the soot, what's remaining is ash. That ash is then analyzed and we can identify the root cause of that ash. And the ash itself is what starts to accumulate up in the DOCs and the DPFs and plugging things up with ash plugs. Now our goal is, since it is a filter and it does have to be changed at some interval, we have to know what those intervals are. So if I could identify, in this particular slide here, the left column on the red is something referred to as an ash fraction, or a soot, if you will. And off on the right we have ash that remains after the regen. So when I have a brand new vehicle and I'm driving it, you'll see most of the soot that's accumulated inside the DPF can be burned off, very little ash left. However, over time, and the EPA requires 150,000 miles minimum under normal conditions, that you should get a life expectancy out of a DPF. And by 150,000 miles, we're looking at about an 80% ash load, things that normally won't burn off under normal conditions, minimum. Now they can go beyond that. Our goal is, if we can clean these engines up, use a good quality oil with a low NOAC volatility, keep the oil from burning, we may reduce the ash load to extend the life of the filter. So instead of going at a 80% load, maybe we're at a 20 or 25% load, and you go a little longer. Now, food for thought for those of you who are going against competitors with fuel additives. 1 part per million trace of an element of a metal in the fuel is equivalent to 1,000 parts per million inside that oil, because you're burning a ton more fuel than you are oil. So if you got an additive out there by a competitor that's claiming you can improve fuel economy, what's the additive made of? Most of your customers don't even bother considering that. So what are those service intervals for the DPFs? Well, on average, you're going to find out that most of them, if you just look at it as a rule of thumb, and guys ask me all the time what typical life expectancy is, about 200,000 miles. On a severe service, maybe 75,000 miles. Now, I compiled a chart for you, and this is available online. This is from the OEM. Recommended intervals for servicing these things, and you'll see they have severe service or highway use. These are your 2 charts that are laid out for you. So if I've got a vehicle, and I was with the guys that were over there in Canada, and we're working on a Cat C7 engine, Caterpillar. Life expectancy in a normal use is 150,000 miles, but we're in school buses, so it's an 80,000 mile life expectancy in the DPF. Some of these buses had over 200,000. Be careful when you're doing the services. Otherwise, it'll come back and bite you in the bud. You're going to wonder why I did the 9300 service and it had no impact. You need to pre-qualify the vehicles. You need to pre-qualify the shops. Now, during regen, there are 2 ways to burn these things off. One way is to inject fuel directly to the cylinder, called cylinder dosing. The other way is through an after-treatment device. Now, your cylinder dosing itself is when I'm going to turn around and actually turn and inject around when the exhaust valve is open, and I inject fuel into the cylinder. And as fuel goes in the cylinder, some of it's going to be pushed out the exhaust, but there's no compression because the exhaust valve is open. You remember, we need the compression to keep those rings sealed against the cylinder, while some of the fuel gets down into the sump where the oil's at. What does that do to your volatility? So some of the manufacturers are installing after-treatment devices located in the exhaust string. This particular one's got a spark plug locator. It's called an ARD head. The ARD head itself is designed to inject fuel in the exhaust after the cylinder, so I don't have fuel dilution in the sump, and I'm not going to make oil. Now, how much fuel is used during a regen process? On average, typically, you'll see a typical usage of fuel, if you're going through a year or a month or a week, 4.5% to 7% of the fuel used in a diesel engine is used for regen. And it doesn't include the back pressures, because we have soot accumulating another 2 to 3%. So you may have up to 10% of fuel used in any vehicle is used for regen. So on a 50-gallon tank, 5 gallons is for regen. And what are they paying for fuel nowadays? $2? 5 times 2, $10 used to use to regen, not to move the vehicle down the road. So if we could reduce regen frequency and duration, we can reduce fuel consumption. So what determines regen are typical things like computer algorithms based upon fuel consumption, or a programming based upon sensor input, or maybe a button on the dash. Some types of sensors that you're going to see out there, one particular one is called a DPS, or a differential pressure sensor, located before or after the filter. As a DPS itself is measuring pressures, it's looking at the diesel particulate filter, and as exhaust gases pass through the channel, soot starts to accumulate. And as soot starts to accumulate, those channels start to restrict, get smaller and smaller and smaller. And this is something that's been proven out there in the field, that the pressure drops across the DPFs are not very accurate, because as those channels get smaller, it's like a water hose. You're squeezing a trigger and you're tightening the water up, you have an increase in pressure. So they add more sensors on there, like temp sensors and soot sensors and NOx sensors. All those sensors and the reasons why they're going to regen is located somewhere in the onboard computer. The onboard computer itself, it will tell you whether it's been triggered by soot or pressure, or the operator mashed a button on the dash. So now we discussed soot, its root causes, and the impact it's having on after-treatment devices. Let's talk about some of these solutions. Some of the solutions we're dealing with there is a 9700 tool. Please don't neglect this. It's an awesome tool. Does a phenomenal job. One Motors Magazine Top 20 Tool Award in 2004, and it's hooked up to the typical fuel system supply and return line. I know we all like to go right directly to the 9300 tool, but I like to tie the two together with our oils. A 9300 tool won 2015 Motor Magazine's Top 20 Tool Award and has an adapter that looks very similar to the 9255 adapter hooked up on the intake. However, we've got more adapters based upon the engine size. The adapter itself is not hard to hook up on the truck. If you haven't seen this before, it's just like your 9255 tool, but those two hoses themselves head on down into the machine. Cold air tube hookups less than 5 minutes. What's important though when you're doing this type of service is to notice when you're hooking it up where the air brake is, or Jake brake on some of these diesel trucks. Are you going to be hooking up before or after that Jake brake? If I'm hooked up after the Jake brake, I won't have a problem, like on this particular setup. But if I'm hooked up before the Jake brake, I got to be mindful of a tube that goes on down into the exhaust. Some guys are installing corks in that little tube. If that cork's installed that tube, guys, that cork can get sucked into the engine. It's already happened a few times out there. So please be mindful of that. I want to wrap this up. Selling to your shops. Your first one here we're dealing with there is the kit itself. And I've always asked two questions. First question I ask to my shop is, what challenges do you face when you're trying to force a regen? I sit there and I listen to them. They'll tell you things like, I got to have it outside at 2,500 RPMs and sounds like a jet engine. The second question I'm setting them up is I'm setting my goal or my target. If I could do this in the shop at 1,000 RPMs, would you be willing to use the service? And I now have a target. So if I do my demo in the shop at 1,000 RPMs, I can force them to regen. I hit the target, they'll buy the equipment. That's selling to your customers, but now your customers have to sell to the end users. The end users, you need to tell them or educate them what the candidates are. Regen issues, EGR cooler issues, the vehicle's application like a school bus or an ambulance or sanitation truck. Look for evidence in those system components. Those are all candidates for the service. So once again, we discussed soot, its root causes, after treatment devices, and how do you sell the products. If you have any questions, I'll be online for a little bit afterwards, but otherwise, thank you for your time. Appreciate it. Okay, I think we had a couple of questions here.
All right, first one. Are there new government standards or requirements associated with the newer and better DPFs?
Are there new government requirements or standards?
Are there new government standards or requirements associated with the newer and better DPFs?
Yes, as far as the emission quality standards have tightened up even more so. The question is so we have a Tier 4 final emissions. Tier 4 final emissions means we have less particulate matter heading out the tailpipe. And in 2016, we have a lot of people out there still circumventing these systems. You can't do that. Even on older systems, you're going to find it required to install the DPF on vehicles that are not equipped with them. So there's a lot of companies that are creating aftermarket DPFs. But these newer DPFs are extremely efficient, up to 99% efficient. And if you can think in your mind's eye, when I'm looking at an exhaust system, in the exhaust system, you got the smoke heading out there. You should not be able to see the smoke. You should not be able to see soot, especially in these newer trucks. Some of the older ones from 80 to 90%, if you're in the 80% range right there, you might be able to see the opacity still on some of those older DPF systems. But yes, there are new systems, new requirements that are out there. Another question?
Yeah, we have a question. If a diesel engine doesn't have DPF and has EGR problems, Do you recommend to use 255 or 9300?
255. If you do not have a DPF, 255. The chemistry between the two, 255 part number and 258 is different. The 258 is a hydrated formula that allows DPF to run cooler so we don't overheat it while we're doing the service. So definitely if you do not have a DPF, I wouldn't suggest using the 9300, use a 9255. And at this time we're going to keep the two the same, separate services. And can I use it for the EGR system? Absolutely. 9255 does a real good job.